Today we're going to look at quantitative electrolysis, okay, and there are a few different applications of electrolysis that we're going to talk about. The first application that we're going to talk about is electrolysis for purification. Okay, electrolysis for purification. For example, if we were to look at the purification of copper, right, we're looking at the purification of copper. Let's say I have an impure copper sample, or let's say I have an impure copper sample. Okay, and what I want to do is I want to extract pure copper from this impure copper sample. Okay. So here I have impure copper, right? I have impure copper, okay, and I want to extract copper from this impure copper sample, okay. So what I'm going to do here is I'm going to use copper. I'm going to use pure copper metal at the cathode. Okay, I'm going to use pure copper metal at the cathode. What I'm going to do is obviously this will be in a solution, right? This will be in a solution, right? And my electrolyte will be copper sulfate aqueous, okay? And then the impure copper will be the anode, okay? The impure copper will be the anode, okay? In the case of an electrolytic cell, that will be positively charged, right? And the pure copper will be the cathode. Okay, the pure copper will be the cathode. Okay, so this is our pure copper. Okay. So what's happening here is that obviously electrons are flowing from the negative towards the cathode, right? So they're going in the way I've shown it here, right? It'll be going in the clockwise direction, right? So we have flow of electrons in this direction, right? We have flow of electrons in this direction, and what we're going to have at the cathode, right? We're going to have at the cathode is we're going to have copper metal deposit. Okay, we're going to have the deposition of copper taking place at the cathode, and at the anode, right, we have impure copper present. What will happen at the anode is that the impure copper, or the copper present in that impure sample, will undergo oxidation. Okay, the copper present in that sample will undergo oxidation, right? So that is going to be our anode, right? So one way to think about this is basically we have this impure sample of copper, right? Again, right, we have this impure sample of copper. This is our anode, right? This is where oxidation takes place, right? This is where oxidation will take place. So this is our anode, right? And when oxidation takes place, right, the copper metal is converted into copper ions, right? So copper ions dissolve in, right, the copper metal dissolves in solution to form more copper 2 plus ions, right? And then the copper 2 plus ions in solution undergo reduction at the cathode and deposit to form copper metal. So over time the mass of the cathode increases, okay? And over time the mass of the anode decreases, right? And obviously what also happens in this process is that right, we have impurities, right? Impurities collect at the bottom of the container, right? The impurities collect at the bottom of the container. So again, the copper in the impure sample undergoes oxidation, dissolves to form copper 2 plus ions in aqueous solution, and these copper 2 plus ions undergo reduction at the cathode, right? Obviously, as these copper ions here undergoing oxidation, right, we have loss of electrons at the anode, and then we have gain of electrons at the cathode. The copper 2 plus ions accept electrons at the cathode and deposit to form copper metal. Okay, so what we have here is, over time, what happens is that the mass of cathode increases, right? The mass of the cathode increases. This is our cathode, right? The mass increases, and over time the mass of the anode decreases, okay? And the loss in mass, right, of anode, right, is obviously, the loss in mass of the anode will obviously be greater than the gain in mass of the cathode, right? Because at the anode you're losing copper, and you're obviously depositing. What's important to note is that however much copper is lost from the anode is going to deposit at the cathode, okay, and the concentration of the electrolyte pretty much remains constant throughout. Okay, it doesn't change, because for every 2 electrons that you lose at the anode, right, 2 electrons will be gained at the cathode, right? So however many copper ions are formed from the anode, right, will be equal to the number of copper ions that deposit to form copper at the cathode. Obviously, the total loss in mass at the anode will be greater than the gain at the cathode, because you're losing that copper plus impurities, whereas at the cathode you're only depositing copper. And obviously, the reason we use pure copper here is because, right, we want purification of copper to take place, right? So we're essentially, what we're doing is we're just depositing more copper on the already pure copper, right? So we're essentially increasing the mass of copper that we have. So we're extracting copper from this impure sample. So now let's look at a question. Okay, the question is, calculate the mass in grams of copper produced at the cathode when a current of 1.5 amperes is passed through a solution of aqueous copper 2 sulfate for 3.25 hours. So the first thing you would do here, okay, the first thing you would do is you would calculate the charge. Okay, the charge Q is equal to IT, right? That's the current times the time in seconds. Remember, for this formula we use time in seconds. So we're calculating charge in coulombs, right? So this is equal to 1.5, right? That's the current in amperes, and then the time in seconds is 3.25 times 3600, right? Times 60 times 60, right? We're converting from hours to seconds. So over here the charge comes out to 17,550 coulombs. Now if you guys remember, we learned that 1 mole of electrons has a charge of 96,500 coulombs, right? That was Faraday's constant. Right? So we can find the number of moles of electrons, that carry a charge of 17,550 coulombs, right? Right? This is basically using the formula Q is equal to NF. Okay, Q is equal to NF, where N is the number of moles of electrons, F is Faraday's constant, and Q is the charge, right? So we have 17,550 is equal to the number of moles of electrons times 96,500, right? That's again this unit. You can use the unitary method, or you can just use the formula, right? And then we get N is equal to 0.1819 moles of electrons. And now we can calculate the number of moles of copper. Right? So now that we know the number of moles of electrons, right, we can calculate the moles of copper. We know that at the cathode, copper 2 plus ions, right, gain electrons to form copper metal, and we know that we have 0.1819 moles of copper, 0.1819 moles of electrons. The number of moles of copper is simply 0.1819 divided by 2, and that will come out to 0.0909 moles of copper, right? And therefore we can say that the mass of copper is equal to the number of moles times the molar mass, right? That's the relative atomic mass. So it's going to be 0.0909 times 63.5. So here we get the mass of copper as 5.77 grams. Okay, so that will be the mass of copper. That will be the mass of copper that deposits at the cathode.